second session of NLP Track. Our next speaker is Dr. Kfir from Basis Technologies, and he's going to talk about AI in any language, using deep learning to build truly global NER. Thank you.
Thank you, Eran. So, again, I'm Kfir. I'm working for Basis Technology, and we're based mostly in Cambridge, Massachusetts, with an R&D office here in Tel Aviv. And we're working on building tools, different NLP tools for processing human languages in different languages in different levels. And one of those tools is named entity recognition, which is what I will talk about in this session. So first thing first, named entity recognition is about finding names of people, organizations, locations, and some other types in just running text, free text, written in different languages. Let me give you an example. Elon Musk says building the first sustainable city on Mars will take 1,000 starships and 20 years. Okay, so Elon Musk is highlighted in blue. It means that it's a person entity, and Mars is a location. And this is the kind of output that we want to get. I mean, given this text, we want to see all those names detected, and then also the type of each one of those detected names. Now, maybe some of you think that it might be a simple task, right? Maybe we could just compile a list of location names, for example, people names from Wikipedia or something, right? And then use a simple lookup procedure to find instances of that list in the text, and that's it. But then you wouldn't know, whether Mars is mentioned as the location, right, or the candy bar. You really need the context to help you resolve these kind of ambiguities. Let me give you another example. So Israel has since become most associated with, try to complete this somehow, citrus fruits, right? It's pretty popular these days. So it's actually the state of Israel. It's a name of a location, right? But if we give it a different ending, let's say this, jazz pianist Bill Evans. So now Israel is not really the state of Israel. It's actually a name of a jazz standard played by this guy, Bill Evans, right? So it's all about the context, right, that will help you resolve the type of ambiguity and to detect the particular name. Another example, so before 2017, if you would say BERT and Elmo, probably you're referring to these guys, right, from Sesame Street, but after, probably referring to these, autoregressive language models, right, that people use these days to solve almost every problem. And we'll get back to at least one of them. So here we add the time dimension, right, to help us resolve these kind of ambiguities. So named entity recognition is probably one of the most important tasks for NLP, or especially if we're talking about information extraction. And it all begins with names, and then you can try to fill in the gaps, find different relationships between names sometimes, sentiment toward the entities, events that they participated in, and so on, right? But it all begins with names, and in this sense, I would say that names are kind of the backbone of a document or a collection of documents. I hope I convinced you that it's a non-trivial task, and it's an important task, right? And but there are related tasks like pronominal resolution, like finding those pronouns and connect them with the real entity mention, and entity linking, right? Grouping together a few name variations for the same name, for the same entity. Entity resolution, which is kind of similar. It's finding or connecting entities, entity mentions with real identities stored in a database or a watch list, for example. But let's focus on the recognition task. So most of current NLP research is done on English, right? That's for the most part. There are works on other languages for sure, but for the most part, it's all about English. And Basis, we're interested in processing other languages, not just English. And they introduce new challenges. Let me give you some examples, right? So this language, Hebrew, most of you know Hebrew here. So that's a highly inflected language, right? So words can be inflected for different numbers and gender, person, and so on. And there are those prefixes and suffixes that we attach to the words. And like here, you can see all the names, right? I probably missed a few, but all the names in English, and highlighted in red, sorry. And then in green, you see the prepositions and conjunctions that we actually need to remove from the names before we send them to the final output, right? But it's pretty challenging because you don't really know whether they're actually part of the name or not, right? Especially if you're talking about foreign names. This is, who knows what language this is? That's Finnish. Okay, so Finnish, yes, it's another interesting language. So with Finnish, there is a problem like other similar languages. There is a tool for building new words, generating new words using noun compounds, right? So you can take two nouns and then combine them and create new words. You can do that with sometimes with proper nouns as well. And that's challenging for a named entity recognizer for sure, because those are all new words. And this is Korean, yes. So Korean has so many challenges. Let me just talk about one of them. So in fact, it's not just one language. There is South Korean and North Korean. And there is a debate if they are actually dialects. But one of the things here is that South Korean is more affected by Western languages. And one of the effects is that people use more space delimiters or space character to indicate word boundaries. And it's inconsistent, even more than in North Korean. And it begs the question, what is a language, right? So is it a dialect, a register, a genre, a domain maybe, a style, right? There are so different levels here, and I'm less interested about answering this question from a political point of view or from a linguistic point of view even. I'm only interested if I need to build a model for one language, or I can share them or share that model across different, whatever we call them, variations languages. Let me give you the final example here. So this is Arabic. Arabic has this real thing that is called diglossia, right? So where you have this modern standard Arabic, the official language. So people learned it at school, but then there is the local versions of Arabic, what we call dialects, right? And they're pretty far from each other. They're pretty different, even more like Syrian and Egyptian, they're more different than each other than French and Spanish, for example. But we still call them Arabic. So let me give you an example here, just an anecdotal example, right? So who knows Arabic and can translate this, for example? Yeah, so it's a simple expression, but it depends who you're asking. So if you're asking a Syrian speaker, he'll tell you, God bless you, or thank you. But in Moroccan Arabic, it means, I wish God will burn you in hellfire. So it's that different, okay? And there are many such anecdotal examples. Okay, so a common environment for solving this problem, or at least addressing this problem of named entity recognition in general, looks something like this, and that's where we use multiple engines, right, to handle that problem in a way. And then we collect the results from the individual engines and send them to a decision-making component for generating the final output. But you see here the AI engine, that's the most important engine, probably. It's a machine learning algorithm that you train with supervised data. But sometimes it tends to fail on those corner cases for which you don't have enough examples. So we combine that engine with dictionaries and rule-based engines that take a kind of a more, I would say, direct approach for the problem and add more flexibility. But let's focus only on the machine learning part. So, and let's talk first about, discuss the difference between traditional machine learning and deep learning in the context of named entity recognition. So with traditional machine learning, you begin with this text, right, and on the left. And then the first step would be to extract features, right? We want to extract some features. So first we break the text into words. Maybe we run some part of speech taggers. depend on the language that you're working on. Lemmatizers, right? So for Arabic, Hebrew, that can be very helpful. Maybe we need to break to deal with all those non-compounds in German, in Finnish, in Hungarian, different languages. Well, once we're done, and we invested a lot of time in designing those feature extractor, we can vectorize everything and send them to a training procedure, a traditional machine learning training procedure for generating a model. Now, with deep learning, the key thing here is that we don't have this feature extraction step. That's very good for us. You go directly, right, from text through embeddings to this mathematical representation, hoping that it captures some of that information that you have on the left, maybe more than that, right? But you use that as input for deep learning model, deep neural network, many layers, different configurations, different architectures, right? So in this sense, deep learning for us at basis, it's just it's much more generic, and we can build one model for one language and then use it on other languages. So a common architecture for named entity recognition looks something like this, right? So it's based on a recurrent neural network or a specific flavor of it, let's say LSTM, right? So long short-term memory. There are other networks. And here we break the text into words, right? And then every word is encoded with a vector, let's say embeddings, word-level embeddings. And then that vector goes into this RNN component, or LSTM in this case, that encodes information or sequential information that comes from the beginning of the sentence, right? And every word in its turn can contribute more information to that vector. And that vector also goes into the last step on top. That will be the decoder, right? So the decoder is just a simple dense layer, let's say, that gets this vector as input and then predicts a label. The labels could be, any one of the entity types that you're working with in your data set. And we also distinguish usually between the first word of a name and then the rest of the words, right? So for example, BERT, that's the label for beginning, like the first word of a person entity, and so on. Other, it's for names that are not, words that are not part of any name. Then you can add another process that goes from right to left, right? That to capture information that comes from the end of the sentence all the way to the beginning. Okay, and then we can take the two output and encoded vectors at each time step, and then we can aggregate them. Maybe we can just concatenate them, do whatever you want with them, but then just get one vector into the decoder, and that's it. One more thing that you could do, you can also, stack together a few such networks like this, right? So the output of one is the input of the next one, and by that you just use or you add more features or more weights, right, and more nonlinear functions. Maybe that will fit better your data set, but it will also slow down your inference procedure, and that's important. We'll get to that very soon. Now, one thing to notice here that we had, I just said that we break the text into words, right? Now, keep in mind that there is a lot of information that exists on the character level that you want to consume, like capital letters, for example, in English, right? That could be a very good indicator for names, and maybe the definite article in Hebrew might help you to identify non-names, and there are some case markers in Russian and Spanish that can be very helpful. And also, there are some languages that breaking the text into words is not that trivial. So, Hebrew and English is pretty trivial, but what about Chinese? So Chinese, you don't have any space characters between words, and there is a lot of ambiguity going on there. In Japanese, less. So in order to break that into words, you need to use like a machine learning tokenizer, right? So like a noisy tokenizer that will introduce some errors that will probably propagate all the way to your named entity recognizer. So in order to compensate for all that, we typically add another component that encodes characters as well, right? On the bottom there. So you can do it with any network that you want, right? With a convolutional neural network, or here it's just a BioLSTM. But basically just take the output of that network, like two vectors in this case, and concatenate them with the individual word level vector, and then you get your word level representation for this particular network. So that character encoding helps. You can see here we measured this at basis with our own data sets for a few languages. Here, I'll show you English, Arabic, and Korean, very different languages. Each introduce different challenges. And you can see that the first row here is just an RNN architecture without word encoding, and the second one is with. And you can see that it's better across the board. This is F1 score measured on the evaluation set. So apples to apples, just adding the character encoders. So that's very helpful, and that was expected, right? Overall, if we compare our such an RNN network with different tricks and tweaks that we added, the best that we could get, and we compared it with our traditional machine learning algorithm that at basis we're using for about 20 years. And we know a lot of feature engineering going on there. You can see that with this RNN, no features, nothing, just using those word embeddings and character encodings and so on, you just get better results across the board. And that's pretty cool, right? And I mean, it's more than the slight improvement or even significant improvement. The fact that we didn't need to extract features or work on this, right? Using linguists and people who actually speak the language. So that's great. So stay positive for now, but soon we'll talk about speed. Another architecture that I wanted to show is a pure character-based architecture. And that's for languages for which you don't have spaces between words, like Chinese. So we just try that. Let's just not using words at all, just use characters, okay? Pure character-based architecture. And you can see for Chinese, it's getting very close. So like 1 point behind maybe from a full token-based and character encoder. And that makes sense because most of the information exists on the character level, especially for Chinese. Many of the Chinese words are actually of a single word length. Okay, so what about speed? So speed, some bad news. You can see here. RNN is much slower, okay? Like these numbers will tell you by how much they're slower than comparing with the traditional machine learning. We are using structured average perceptron, but it doesn't really matter. And in fact, we implemented the traditional algorithm on a platform that cannot benefit from a GPU. So this is everything compared on a CPU. And the RNN here is implemented on a TensorFlow serving in Java. So just for the sake of completion, we tested this also on a GPU, only the RNN part, and you can see that it's faster, but it's still dramatically slower than the traditional algorithm. And it begs the question whether these models are ready to go live and solve real-life problems, right? It's not just about research, it's also about solving problems. And I don't have a good answer so far, but we're trying different ways to expedite these algorithms. They try different architectures, right? But I can tell you that potential consumers of these models, they don't really care about those slight improvements in accuracy. I mean, we're getting excited about this, but they don't. They more care about speed. They care about domain adaptation, the ability to take one model and transform it to work better on a different domain with almost no data. They don't have time to annotate, right? So those are the problems that we're trying to focus on rather than just improving accuracy. And I'll talk about one of them right now. So, to build a tagger for one language, you need annotated data, right? So you need to annotate data for that particular language. So you need, these are the languages that at basis we have models for currently. So it means that for every language here, we had to recruit native speakers, right, to write annotation guidelines, go through this annotation process, adjudication. That's a lot of work. It's very expensive. And we're always looking for ways to expedite this process and make it faster, cheaper, and support new languages to increase our language coverage. That's always required. And specifically, support low resource languages. So let me talk about one experiment that we're doing these days. I'll share with you some preliminary results, but still work in progress. So we're going to use these models. And sometimes I feel like this. They're coming very fast, all these autoregressive models, right? And we're going to use only one of them. So BERT. BERT, as you probably know, it's just based on transformer. It's a huge language model based on transformer. And transformer is a bit different than what I showed you before. It consumes more attention links rather than recurrent links that I showed you before. But I won't go into the details. Just will say that there are two steps, main steps with training BERT. One is training or pre-training, right? In this step, you take many documents, plain documents written in English, for example, and then you run them through the BERT model, and you train BERT to predict a word given a context, right? More or less. And once you're done, you have that model, and you can connect it in the fine-tuning step. You can connect it to a classifier that solves particular downstream task. And then you train the whole thing together with your data that you have, the annotated data that you have for that particular task. And while doing this, you can also adjust the weights of BERT. And this is why we call this fine-tuning. So there is another version of BERT. It's called multilingual BERT. And here you take BERT and you run documents written in different languages, in about 100 different languages, typically using Wikipedia pages. And what's interesting about this is that you don't need to identify the language because you're using the same tokenizer for all these languages. It means that they break the text into subwords, okay? So it's not a morphological, a linguistic tokenizer. They just break the text into subwords, and there are some subwords are shared across different languages. So one subtoken that is shared across two different languages, for example, will have the same unique ID, and everything will be placed in one vocabulary. So it means that languages that have similar, or at least high rate of similar subwords, they're probably similar in the context of MBERT, and they can benefit from each other. Okay, so what we did here, we took MBERT and we trained it or fine-tuned it on the NER and identity recognition data, annotated data that we have for many languages. Here I just show you 8 languages, different languages. And you see here the F1 score, measured on the evaluation set. Pretty good scores, but I didn't compare them to the state of the art or something, right? Doesn't matter for this case, in this case. And on the other hand, we just took MBERT, the same thing, but without doing any fine-tuning at all, just trying to predict labels using a random classifier. So the same architecture, but untuned. And you can see that it's much worse than the blue bars here, which makes sense, right? I don't know what happened with Russian there. We need to check that. But here, we took MBERT and we fine-tuned it only on English. Okay, so no other languages, only on English, annotated data that we have only for English. And then we predicted names for other languages, for all the other languages, right? And we evaluated the model, the English-tuned model on all these 8 languages, and those are the yellow bars. And you can see that at least for French and Spanish, it's getting closer, right, to the blue bars. And that's pretty exciting, right? It's interesting. You clearly see that, for Hebrew and Japanese and Koreans, it's not that good. But don't get too excited, because what we show here is just, we call this thing zero-shot prediction, right? I showed before. But if you had only 10 documents annotated for each of these languages, like French, Spanish, you could get even closer to your state of the art, right? So you didn't need all that fine-tuning and do zero-shot. You just need 10 annotated documents. Not that easy to get, but still it's not a lot, and you can get closer to the state of the art. Of course, if you had more documents, you could get even closer and closer. So the good news is that with BERT or MBERT, we don't need as much annotated documents as we needed before. And that's very good news. So let me conclude this session and leave you with this. Named entity recognition is not just about improving accuracy. In fact, it's more about, or not more about, but it's also about maintaining reasonable inference time. It's also about domain adaptation, which we haven't covered here. And it's also about increasing language coverage. I mean, there is a surge in demand for new languages all the time. We get them all the time. And we need to find better ways to do that. So thank you so much for listening. Yes. So morphological features, as far as we can tell from the traditional machine learning algorithms that we have, they are helpful for this task, especially not just for detection, but also for what I showed before, normalization. So like extracting the names out of those morphological features, right? Or removing all these prepositions and so on. Yeah, they're very helpful for that. What do you mean by content? So maybe it's a good idea to try to, you said, to combine languages, right? And try to benefit one from another. I think in the last experiment, we're actually doing that, but we're still not sure what we're doing there, right? So we need to take a better look at how the model looks like. For example, to count how many shared subwords there are, that's one test. Or maybe how many n-grams are shared, something like that. Yeah. We're not doing, we're not using grammatical features here, only morphosyntactic features. So, to some extent, that's syntax.
You mentioned that we use GPUs output was slower or a lot slower. Were you guys using GPUs public cloud?
Yes.
Not on-prem?
No, public clouds. Those experiments were done on public clouds. But I don't know. We can try. I didn't think about this, but yeah, maybe.
Okay, thank you, Kfir.
Thank you.